Yeah, no, I mean, technically this part is more like overall. I don't know if everybody is going to.
Yep.
People from the third world.
Yeah. Okay. Hello, everyone. Hello. Right. Okay. Thank you all for showing up today for a quantum communication panel. I'm the Events Lead for the Society, and today we have two distinguished speakers with us. I'll just give you a brief introduction for each, but I'll let them introduce themselves upon their chances. We have Dominic, who's a professor at the Engineering Science Department, and he's head of the Optics Communication Lab. He's also the director of the National UK Quantum Computing Hub. We have Emilio, who is a specialist research professional from BD's Applied Sciences Division. And we have Wenmiao, who is the director of business for Quantum Dice and also based in Penang. And we'll have all of them taking turns explaining a presentation, followed by an actual demo of a random number generator from Quantum Dice. So without further ado, let's begin. Pass over to Dominic. That's my
Whilst he's getting the slides ready, let me just introduce myself. I'm Dominic O'Brien, and I've probably been here in Oxford since before many of you were born, I imagine. So over a quarter of a century now. So I'm in engineering science. I'm a professor there, and my interests are in optical communication. So that's using beams of light through free space from here to here to provide Wi-Fi using light, if you like, but also to do quantum communications. So we started classical communications, and more recently we've moved into trying to transmit single photons from A to B. Now, of course, this is successful these days. There's been demonstrations of communications from a satellite to the ground with less than one photon leaving the satellite and getting down to the ground. So some fairly impressive stuff. Ours isn't that, but I'll just show you what we've been doing. Let me just have a look at my timing. See when I started, 1709. Okay, so I thought I'd just tell you a bit about quantum technologies in the UK before I started. So I have a role as I'm director of research hub in quantum computing as well. So this is a map of the UK. You can see 4 blobs there. Those are research hubs, and those have been running since 2014, looking at quantum technologies and how we might be able to use them. There's one in imaging, that's the red one, based furthest north in Glasgow. There's one in communications, which I'm a member of, and we're talking about today. That's based in York. That's the next one down. There's one in Birmingham, sensors and timing, so things like very precision atomic clocks, that sort of stuff. And there's us based in Oxford doing quantum computing. And there's also a National Centre for Quantum Computing. There's a big science site about 15 kilometres south of here at Harwell, some of them know that. And there's a quantum computing centre being built there. So it's pretty vibrant in the UK. So this is my career, trying to sell quantum as a career for you, because there's lots of opportunity at the moment. It's a very vibrant field. We want really lots of people to come in and work in the area. So if you're interested at all, ask me afterwards. But there's a lot going on, not just in the UK, globally. It's a fairly exciting area to be in. Anyway, onto the meat of the talk. So what about quantum communications? Well, we rely on secure internet communications, on encryption keys. There are 2 sorts. There's a public-private key. So I can give you a public key, and you can encrypt something, and I can decrypt it with a private key. And then there are symmetric keys. So we both share a secret. We go away from each other, and with that shared secret, we can then communicate securely. And those are all enabled by factoring long numbers. The problem with quantum computers is that they can, in theory, when we get many more orders of magnitude qubits than we have now, break that encryption. So one way of helping with that is to use quantum communication. So we go. So the link is, you can send streams of single photons. That's what people do at the moment to represent. And it's an interesting process, which I'll tell you about a bit. Except, right, we're back again. So the link can be protected against eavesdropping. It's provably secure if you do it right. And people have done it for satellites, thousands of kilometers. There's a fiber-based network in the UK, which I'm sure the next speaker will tell you about. And we've been interested over quite short ranges. So looking at handheld to handheld devices largely. We've done a bit to drones, and I'll talk about that in a second. But from an engineering perspective, it's just an optical link. It's a beam of light, but without many photons, very low power. And it's about getting as many photons from here to the other end. That's what it's about. So just to tell you a bit about the process, there are several schemes you can see listed at the bottom of this. Let's see if this pointer works. No, never mind. Okay, so basically we use a scheme called BB84, which is polarization based. And so you've got Alice, who's your transmitter. That's always called Alice, and Bob, who's the receiver. And the person in the middle you don't want to get information is called Eve. And what Alice does is transmit one of 4 optical polarizations. So that's just the polarization state of the photon that you're sending. Bob does a series of measurements on what he receives, and they exchange information about the measurements. And from that, they can share a secret. They can distill a secret key. It's not as if Alice sets out to send a known sequence of numbers. It's actually Alice sends something random, and they just talk about what they sent and what they got. And by talking about it and exchanging information, they can get a shared key. So that's the sort of quantum encryption side of it. The key thing for us is that we need to be able to send one of 4 polarizations, and we need to make sure as much light as possible gets from Alice to Bob. So that's what the talk's largely about. It's the engineering side of things. So these are really just snapshots of things we've done. So this was work we did actually in collaboration with a few people, looking at how you could communicate with a drone to a base station here. So the idea is the transmitter on the drone, that's going to send a stream of light down, pointing at some base station. And the challenge is there, so you have a really narrow beam of light. You need to point it in the right direction to get to the receiver. And the receiver also needs to point back at you, so the light is received. It's like looking at something with a pair of binoculars. Even though light can get to the binoculars, you need to align the binoculars. So you need to point both ends of this link. So we've got this link coming down here. You need to point both ends. There's also a synchronization challenge, because you're sending a pulses of light every now and again. That represents the information. And your detector needs to know when those pulses might arrive, because otherwise it will just be picking up noise from the environment. So that's a problem, and synchronization with QKD is a big problem. And just to show you some of the things we did for this, just to show you some of the engineering. Right, somebody needs to come and help me here, because this seems all frozen. So just to show you, I'm not going to talk about, we did a couple of things on this. So we built a radio to synchronize the UAV side. You can see at the top left there, to the ground station side. So the other thing to notice about this, so the bottom is all about the radio. Don't worry about that. I'm not going to talk about that too much. The top side is about the QKD. So you can see in the middle, there's a red beam of light. And that's the QKD data. That's not enough, because you need something to run the tracking. And pretty much you always tend to have other beams of light. So if you look, there's a tracking laser, the green light below, And that's a much more powerful beam of light called a beacon at the same, pointing in the same direction as the main one, but much, much brighter. So the receiver can see this bright green piece of light. Well, let's assume it's green, and it tracks off that. So if it's aligned to that, it can actually pick up the quantum information, that red, much dimmer beam as well. That's the beacon at one end. And if you look at the ground station, that's GS on the right there, you'll see there's another laser going upwards as well. So each end has a beacon. So it's like me looking over there and seeing a red light and I know where to point. The other end seeing a green light this end and it knowing where to point. So you need those systems. And a lot of what we do is about doing that. So that was to a drone. The next one is about handheld devices. So the idea is that you might be able to, everyone uses, who doesn't use wireless payments? Everyone uses them, yeah? But there's a sort of security question about that tiny little link, that radio link that just exists about when anybody can get in. And the question is, could you secure that? So what we were interested in we worked with Nokia, it was in this case, to look and see whether we could build a link just over a meter or so, something like that, but a quantum link. So the idea is you'd go to the cash machine and you wouldn't pick up cash, you'd pick up keys, secure encryption keys, hold them in a wallet, and then you could use them for secure banking, that sort of thing. The challenge is this. So if you look at the way your hand moves, if you hold something, this is actually a plot of the hand movement. So here's the angle here versus the time, and it's just wiggling up and down all the time. And this is actually one of my postdocs he was Korean and they have to do national service and he was an armorer, so he had quite a steady hand. So this is quite a good control for this guy. And anyway, you can see how wobbling it is. Anyway, you can characterize the wobble, but the challenge is that wobble is too much without doing anything to maintain that optical link. So again, you need this tracking system. So this is quite a busy diagram. What it shows is you've got the fiber that you can see. Let's see if I can get a pointer up on this at all. Can somebody show me, can you come and show me how I get with this mouse, get a pointer? This is the point. That's bizarre. No, don't worry, it's fine. I need a stick or something. Yeah, so at the top here, the QKD beam is from that fiber you can see where, and that red dotted line is the QKD. And that's going from the kind of one end of this link back to this point here. And it's steered by two things called MEMS, which are little steerable mirrors. And the rest of all of this is about doing the tracking again. So the bit at the top, you can see there's a green light coming out of that top section. And what this thing is doing is looking for that green light, working out which direction it's coming from, and pointing this mirror so the green light is received. The one at this bottom one, you see the brown thing there, that's light going up, that's its beacon. The one at the top is looking for that beacon, pointing its mirror to get that one in the right position. So when you get the beacons, the green and the brown in the right positions, the red light, which is the quantum light, can link from one to the other. So it's a kind of indirect way of getting the light to go in the right direction. So that's what we do. And this shows you what the thing looked like. So it was kind of handheld. So the one at the top, you can see a hand. Bottom, there's the receiver. And this one sent a quantum signal, which was generated by the module you can see on the top left-hand side. So you've got these the things that's called RC-LEDs or LEDs, so they're emitting photons, they're emitting single photons, and they all get combined in all that system there, come out of that, go through the pointing system to the other end, and then they get separated out in this module and are received. So there's not a lot of quantum in this, but there's a lot of engineering, and that's the way these things always work out. But the basic principles are, you get over that bit fairly quickly, and then the sort of nitty-gritty of how you actually get light from one end to the other really is most of your time. So that was version 1. I'm not going to go through that. The next thing we did, this was with the University of Bristol, was try to simplify even further. So that one was like your phone to your phone. This one is like a credit card. So what we did was we tried to remove all of the complex bits from the credit card, which is the thing on the left, and put it all in a box on the right, which we call the quantum cash machine. So this was like a card and a machine. And that means that you've just got to do all the engineering of the link in a slightly different way. So I'll just show you a few pictures of that. So this is the world of experimental engineering. So the credit card, in reality, this is our handheld device. So somebody said, in fact, one of the professors at Bristol said, he said, yeah, that's Hagrid's hand, isn't it, from Harry Potter? So that's handheld. Whoops, that's handheld of your Hagrid. Anyway, that's the handheld bit. What you do with that is you point it at the box on the left, and it can send quantum information between them and kind of exchange a secure key. So it's kind of working now. And it's an interesting question as you're an academic, what do you do then? So we're trying to find a way to find somebody interested in a sort of commercializing this. And I'm sure that the speaker from Quantum Dice will be able to tell you a lot more about that than I will. It's an interesting question. It's kind of got to the point now where it's semi-reliable and we need to send it somewhere else. What I should say is all of these things have extremely low data rates. So I'll show you an experiment. In fact, I'll show you the next one and you'll see what I mean. So what we're interested ultimately in doing is trying to combine fiber systems, so light down optical fibers, with free space. And fibers are everywhere. Basically, you don't really transmit information longer than about, down a wire, anything more than about 10 meters is an optical fiber these days. Just everywhere. Nobody really uses anything else anymore. So this system here, what this does, these two boxes here, is take light from a fiber, gets it into free space, points it, sends it in free space, receives it, and gets it back down an optical fiber. So it kind of breaks the fiber network. So the diagram of how it works in the middle, I'm not going to go through it in massive detail. If you see at the top there, there's an optical fiber. There's lenses to make it a parallel beam. Those are the two yellow beams you can see. And there are these mirrors, M1 and M2, that do the pointing. So light from that fiber on the left-hand side, terminal A, goes down, M1, M2, back into the other fiber. Now that, I'm not going to go through the way those mirrors point. This is what you can see here. The bit at the top, there's a gold thing you can see, that's the actual mirror. That's the bit that moves around. And there's various mechanisms to make that track and point. So let's go to this slide. So what we did was we went to the University of Bristol, where they have very high data rate optical fiber systems that transmit 1.6 terabits per second. So that's, and your Wi-Fi is 100 megabits per second. So what's that? A couple of thousand times faster than your Wi-Fi would give you. But they also put on QKD as well. And how that works is all modern communication systems have many, many colors. So the optical fiber has a particular band of colors that it uses to transmit. You stack maybe 40 or so, or 60 or so, or 100 colors, all carrying separate data streams, all separate beams of light. Now, in this case, one of the colors carry the quantum channel. I'm not going to go into anything about this, but I'm just going to cut to the point I was going to make about quantum transmission. So the quantum data rate, which they call the secret key rate, this is the rate of secure keys you can send, for that system was 2,000 bits per second. So that's sending roughly 2 terabits per second of optical data and 2,000 bits per second of secret quantum data. So the challenge of quantum communications is one of rate. The actual rate that you can send these secret keys at is extremely low compared with the rate you could send conventional data at. And that's simply because you're not sending many photons. Yeah, there's not a lot of data going from one to the other. So that's the real challenge with this stuff. You could never send all your data securely because you'd never send anything. You'd send 2,000 bits per second. So actually what you need to do is combine conventional digital encryption plus quantum techniques to kind of provide this security picture for the whole thing, because otherwise it simply doesn't work. One more slide and I shall finish there. Right, so what I've shown you so far is encryption where I just send a photon of a known state from A to B. And that's point to point. At the end of that link, I have to, if I wanted to send it, let's say that's fine for A to B. Let's say I want to send it A, B, C. B in the middle has to be what's called a trusted node. Yeah, I have to lock it in a box because there you get access to the data. And that's not brilliant for networks. It's good for point to point. Pretty much everything commercial is a point-to-point system these days. And you literally have to trust the node you're in. And you can't always do that. The other way to go is use what's called entanglement. So entanglement is the locking of two quantum states, if you like. And so this is an experiment done by David Lucas in physics. And you see a couple of ion traps. They're trapping ions, and the ions generate photons. And the photons join, go down fibers, which you can see in this diagram here, and they join up in this detection station. And by joining those photons, you entangle. And using that entanglement, you can actually start to think about how you build quantum networks rather than this point-to-point thing. But you need some sort of quantum element in the middle. You need some element of entanglement. You need a small quantum computer to start to be able to create these quantum networks. And it's a big area. People call it the quantum internet, but I think that's bolting together two buzzwords, if you ask me. We're like a million years away from that. We're just in the sort of foothills of the physics to try and work out how you might start to create this. But this is the stuff we're beginning to work on now. Starting to work with David on this and how you distribute this entanglement property through the quantum network. I'll leave it there. Thanks very much. How are we doing questions? We're doing it now at the end.
You can do it at any time you want. Do you have any questions? We can do it now.
Yeah, so you said that this BB84 protocol was immune to.
I'm going to walk. I'm really deaf, so I'm going to walk towards you.
Yeah, no.
You carry on. Yeah.
So the BB84 protocol you spoke about at the beginning, right?
Yeah.
You said that was immune to eavesdropping. Could you explain a bit more why? I suppose?
So I think the basics of it are is if you so you're sending effectively. It turns out, because of the way you generate the photons, you need to send less than one photon per pulse you're going to send. So on average, every one of those polarization states, there's only 1 in 10 of those has a photon in it. And you can think of it, the simplest way to think about it is, well, if I'm sending one photon and somebody intercepts it, there was only one photon. So I don't get it. And I know, because I won't get it, I don't get any fake information, and they don't really get anything from just getting that. There's a more complicated quantum way of thinking about it and says, look, this is a quantum thing. You can't clone a quantum state because if you clone, you have to measure it to clone it. So there are sort of various arguments about why you can't eavesdrop. Now, the simple way I've explained it isn't secure for various reasons, but you can do, there's various protocols to make it secure where you can send some decoy states as well and monitor. You send some other states and you can monitor, you know what you've sent, and if you don't get that, you know somebody's been looking at it. So there are kind of various ways around. The security proofs, I have to say, are kind of beyond what the knowledge we have, really, the real security proofs that you need to do. But there are sort of, at its simplest, you could say, well, I'm sending one photon, if somebody steals it. We kind of know. Yep, go on, right at the back. So you use some, you can buy detectors that are sensitive to single photon levels of light. They're effectively photon counters. Remember I said synchronization was really important? So what you tend to do is you tend to synchronize the detector so you turn it on for a little length of time when you know you should get a photon because you can synchronize it. And so you go, I'm just going to look now. If it was a photon here, there's a good chance it's one I wanted to send. But this is, you know, I said the rate was really low, the 2 kilobits per second. That is simply because often you send, typically you might send might send a photon every, a billion photons per second, say, and you ended up with 2,000 useful ones per second. And the rest of it is the sort of loss and the probability that what you picked up was noise, because the detectors are noisy, sunlight, all of these sorts of things. It's not an efficient process from end to end, but you can. Bizarrely, your eye, if you stood in a dark room for long enough, that is almost a single photon detector. So, you know, sensitive detectors exist that can count these photons. Just as an example, if you've got a really high-end smartphone, smartphones have a detector which, when you put the head against the screen, it turns the screen on. The sensitivity, the touch screen gets turned off. In high-end phones, that's a small LiDAR. It bounces a beam of light off your head, measures the distance. That uses a single photon detector. So you can make them, and they can be quite cheap. There's one here.
So how fast is your switching when you are tracking?
Tracking. So for these handheld ones, the loop, it turns out, I don't know why I remember this number, 40 milliseconds.
40 milliseconds, okay.
Yeah. And that's because when you're tracking, you have to think, okay, how much is it going to wobble in what time? And you have to have understood what you need to steer to in that time so you can steer it back before it gets outside the zone in which it operates.
Any other questions? Okay. No? Okay. I think we can have it. Okay. Good. There's a secure key.
Good afternoon. My name is Emilio Huguessalas. I work for Telecom. I want to thank Blanche and Wenmiao for inviting me to this talk. Very honored and very happy to be here with you. So this talk, I would like to give some discuss a bit on the activities that VT has related to quantum, based on the trials that we are doing, and also some quantum projects that VT is involved. Well, before going into the details of the quantum activities, I would like to give a brief description of VT research environment. So VT takes very seriously the research, and that is protect the number of patents that is in the portfolio of VT, which is over 5,000.
Which is based on, yeah, thank you.
Is better now?
Yep, it is.
Okay. And yeah, well, VT has also good relations with the universities, and also the schemes for graduates, apprentices, VT every year. And most of the research, or the main research, happens in the last part, in Houston, in Stockholm, UK. And in this part, well, there are around 4,000 staff doing different activities, including VT people, as well as people from open groups, partners, graduate apprentices. And well, also there's a cluster of high-tech companies in the area collaborating with the research staff. And yeah, I want to just talk a little bit about the history. And so VT started as an electric telegraph company in the middle of the 1800s, and then several milestones happened in this next century, and just around 1980, was founded at Telecom, and well, around the same time, there was the first production of when more towards quantum worldwide, there have been several milestones. For instance, in 1984, presented the PB84 protocol. So in 1984 was created by Bennett and Rasper, this protocol. 10 years later, Peter Shor created a quantum algorithm that was able to find 5 factors of integer numbers, which could be used to break crypto systems based on RSA, DP-Curve, and DP-Hellman. Yes, well, then also other initiatives to increase the number of qubits by different companies such as Intel, IBM, D-Wave is now in the race to increase the number of qubits. And there have been also declarations of quantum advantages from Google and from Chinese groups, doing quite well in this exploration. And well, the aim is to increase this number of qubits to even 1 million. Well, from VT, well, as I mentioned, there's this 140 megabit per second link in 1984. 34 years later, over the same link, there was the first QKD transmission in between Cambridge and Adastra Park over a deployed commercial link. And well, we'll talk a bit more about that. And recently, last year, we explored or evaluated the protocol fiber with quantum key distribution. And probably you heard about this year in April, we launched a commercial trial of quantum secure networking in London. Now I will just when we talk about these trials briefly, describe some more details. As I mentioned, Cambridge to Adapter Park link was launched in 2019. Well, yeah, as it was mentioned by Dominic, we have several trusted nodes in here. In between Cambridge and Adapter Park, there are 120 kilometers of fiber, and in between there are pairs of Alice and Bob to generate these keys. Following not in this case, not the DB84, but the coherent one-way protocol that is based on an equipment of a company which is Quantic that generates these keys, and then if we XOR them all together, we can generate a secure link from Cambridge to Adapter Park. So it's a whole process, but also this link is enabled with classical channels. So we also coexist 5 channels, each of them of 100 gigabits per second over the same fiber. We coexist these channels together with the PKD channel. And well, we use different bands for this trial. On the O band, we use the PKD. On the C band, we use the classical channels. And then, here are a few of the specific rate showing the stability for some period of time. The other trial that we've been involved with is over is together with the technology center in Bristol, which is called the National Composite Center. And this, even though it's very short distance, 7 kilometers, it's very important because it shows how a commercial or deployed link that is a real one that is used by different by actual customers can be also used for a QKD transmission of not only the QKD signals but classical signals. And when this trial, the Toshiba QKD solution was used, and also we used for the encryption the ADVA units to extract these keys and insert it within this data for transmission. Yes, so yeah, this is more detailed how it happens. So as you can see, it's more complex. Unfortunately, we cannot see differentiate colors, but this should be different color. This part, this is the quantum part. That is where the Toshiba PKD unit is, and the keys are extracted by a server, and then the server feeds these keys towards an encryption unit from ADVA. That is the manufacturing cell node that generates the signal from, I don't know, from advanced materials that needs to be transmitted securely to the other building. And that is fed to different building blocks towards this quantum part for intention, following a firewall. So it's already a very complex integration of different components. There is also network and management links to interact with other building blocks of the whole system. The same, well, the opposite process happens on the other end. In the compute node, this data is decrypted and then sent towards the compute node, passing through the firewall after decryption. And in between, there is the optical fiber. It's just a pair of fibers where all these QKD together with the classical channels and control and management is set within this fiber. These fibers, and it's all operated by Overreach, which is a subsidiary of DP. So I also mentioned that we've been working with or exploring the transmission of PKD over a 4-core fiber. But why we want to explore 4-core fiber? 4-core fiber As you can see, that is a cross section of a nested anti-resonant node fiber, where that's the design. By in this case, we were working together with the municipality in Southampton, and the features of the hollow fiber is that it has ultra low nonlinearity, which allows us to transmit higher powers, and that we look at the QKD coexistence, then we can transmit with high power without interfering with into the QKD channel. Low latency, since we're transmitting over there within the fiber, we can transmit 30% faster data within this hollow fiber. We can also explore new transmission bands. So this hollow fiber has better properties in other bands, so we can transmit more data in OL and other bands of the optical fiber. Thermal sensitivity is better, is lower in this type of fiber. So if we transmit, for instance, a timing signal, there is less drifting of the channel. That can be benefit. Can be advantageous for some applications. The low chromatic dispersion is also it's actually much lower compared to the standard single fiber, and that is very helpful because we can use cheaper components, so we can still use the non-return to zero modulation formats to transmit data instead of something more complex like coherent. And yeah, so this overall it improves the performance of an entire backbone network, and we have done some modeling showing that 20% of improvement. It means that we use less amplifiers compared to if we use just the single mode fiber, and that is reflected also in the power consumption. Thank you. And going back to the QKD over this hollow fiber, we did a demonstration in our lab transmitting this QKD consisting with the classical channels. So for the QKD, we use the QKD unit from Dominic, which is as a various unit. That's a carrier grade QKD unit because it includes all the software protocol and it's already everything is included there. And we transmit over a hollow fiber that is cable, that is almost the one that is going to be deployed over a link in the field. So for the classical channel, we use a continuous wave laser source, and then we tune it and we evaluated this coexistence or this cable hollow fiber, and we found that we can achieve up to 10 dBm of launch power of these classical channels, and still our QKD channel was performing well. And the main limitation was the interface between the hollow fiber and the single mode fiber. So there is still a lot of room to explore there for improvement of this kind of trial for the hollow fiber. And as I mentioned, we are now there is work ongoing on this QKD metro network. The aim is to engage with end users, and we are working well with Toshiba, and they are providing the hardware and as well as the key management, and we provide the existing network management operations, and altogether is to explore how end users can be how their data can be included in this QKD network. The idea is also to include the aspects of post-quantum cryptography together with QKD. And we use the optical spectrum access interconnect that they often reach nodes, and that's based on the previous trial with NCC, so it's taking some of the explorations of this other trial into this trial. And you will hear more in the coming months about this network. And now we'll talk about the quantum projects that we are involved in. One of them is QKD over there. So why? Well, I'm already Dominic presented a lot of the free space optics, but for one of the reasons is 5G, and 5G will provide these benefits like high bandwidth, gigabit per second of transmission, low latency machine-to-machine communications. And one issue of 5G is also the densification. So how we want to interconnect many small cells to a macro cell, and to achieve that, there are methods such as the millimeter wave, which can be limited in bandwidth, or can be also with deploying more fibers. But then we need to invest in fiber, and well, the time to include this deployment will be considerable. So why not use free space optics as as an alternative, or together with these other methods? And since we're exchanging data over there, well, let's put QKD also, and that's another, that would be a good thing. So the project that involves these free space optics and QKD is QKD, and we were coordinating this project, and that is aims at different levels of the integration of different aspects for these free space optics QKD. On one level is the quantum components. So companies such as New Quantum is developing single photon sources and detectors, as well as QRLs. Duality Bristol is also developing the quantum readout POC, or physical controllable function, for fingerprints and more security. Systems have the Watt University developing the system, the QKD system for free space transmission. And what we need to transmit, or we are aiming at around 100 to 200 meters of transmission. So for that, Fraunhofer is doing all these mechanical interfaces with telescopes to transmit on over this distance. And well, not everywhere we will have the QKD. We will have then where we won't have the QKD, we can also use other security methods, and that's developed by a company called Angoka, that they are developing this device authentication unit to do the encryption, and we will interface this down to the QKD. And as use cases, well, we are aiming at two main demonstrations. One in Industrial Park, that will be to transmit in between building rooftops these encoded photons for QKD photons, free space. And the other use case is the autonomous vehicles. So we, Warwick University was part of this, is leading this demo that will do this interconnection securely between the roadside, between the onboard unit of the vehicle towards the roadside unit for the lamppost. And so this is the overall picture of this project. So we have interconnection secured between onboard unit, roadside unit, and then to the building, and then between buildings. And on top of that, we have software that will enable do this key management based on QKD, and also is controlled by a SDN. So there is a lot of integration, not only hardware but also software. The other project that I would like to present is the quantum data center of the future, and this project is both projects are funded by the Innovate UK. So this project aims at exploring the gap in between the integration of of data center and quantum technologies. So nowadays it's very well known the integration of data centers and telecom infrastructure, but not the quantum technologies and data center are still usually in isolation. So this is one of the aspects of this project to understand what is required to do this integration. The other aspect is to understand, as we mentioned, the quantum internet. So even though, yeah, that's a big topic and yeah, it's nice to put them together, but what is quantum internet? With this project, we want to understand these building blocks towards this quantum internet. So how mainly how quantum networking will occur, but based on data centers and access to end users. Yeah, you move to this one. So the motivation, this project is quite appears in good time because there haven't been many projects around, but slowly the number of projects that is increasing. And for instance, there's this Equinix and SK Telecom started already with this integration of quantum technologies data center, but it's more on the security or cryptography. There is an initiative in Germany for QDXA that started last year that aims at integrating this quantum computing and supercomputing. NVIDIA is already talking about hybrid quantum and classical computing. Amazon is already discussing this quantum networking, and they already started the research center. And very recently, this Dominic aims at this quantum computing integration with classical computing, led by Netherlands, QTech. So, this is a project that aims at this integration of quantum and classical resources in a data center. And as it is, we were exploring what are the requirements for this quantum data center. So it needs to be data center compliant and has quantum computing modules. And for access, we are exploring the access with a combination of QKD and QC. So in this part, the development of infrastructure as well as a set of requirements and applications is going to be part of this project. We are trying to understand why we need this advanced quantum data center. And on top of this, we are also integrating hardware and software. So there is also a big part of hardware of these two units in the project. So there are several aspects, but one of them is computing. So Orca has developed this quantum processor based on boson sampling, and that is ready to be integrated in a data center for specific applications. And there's already some software development that can be integrated in this part of the project. The other important part of this project is the security, and for that, Kets is developing these integrated units of QKD and trying to get into better footprint, smaller units for this QKD. And this is the overview of the project, the initial overview, where we have a hybrid data center with the classical resources. We have racks, servers. We find nowadays in a data center, all interconnected with top of the rack switches. We are able to have also optical circuits integrating or interconnecting these racks. But on the other end, we have the quantum resources, the quantum processors, and memory, and interface to high-speed electronics. And on top of that, we have an orchestrator to manage these workloads in between hardware and different types of hardware. We have also the aspect of the end users, like NCT also, and this end user will require access to the hybrid data center, and will require also to provide to send some data sensitive, some sensitive data. And for that, well, we're aiming to secure this data with PKD or CPC or both. Yeah, so that is the two projects I wanted to present to you. And well, I will want to conclude that the QKD is moving from the experimentation to the field deployment and looking into more commercial provision of services. QKD is not the entire answer for the security. It's a very strong building block, but it needs to be added with other aspects such as the well, authentication has to be added to this QKD, as well as other integration, secure integration on the nodes. We believe that the network operators have to lead this integration and well, to do these trials of this underlying infrastructure. And well, there are methods also to discover where the quantum internet is going, and for that reason, we are looking at this QKD and QDCF project. And that's my side.
Thank you.
Do you have any questions?
Projects. Who the end users will be and what they're doing?
So end users, I cannot tell that much at the moment, but one end user at the moment is EY, so it's a consultancy company. The others is well, definitely I cannot tell you, but yeah, it's well, any corporation that will require to secure the data can be any end user that is well, feel that their data is not secure enough with the existing methods of encryption, and they could use our network to encrypt all this data with QKD.
Sorry, I suppose probably we should clarify. I mean, is there anything that they can do at the moment that in your environment that we get post-quantum cryptography? Or that makes sense?
Well, is the question more of so? Yeah, you can. There are methods of security already. Working in I mean, internet has security, but the problem is when will you have or when a quantum computer appear? So even though there is not a quantum computer with enough qubits at the moment, but in the future there may be one, and what an eavesdropper or could be doing is just storing all this information and waiting for the quantum computer to appear, and then once they have, and it could be a big problem. Yeah.
You have anything else?
Sure.
Sure.
So the quantum key distribution protocol you use the same as the DB84?
No, this is called coherent one-way.
Okay.
That's a different one. Yeah, it follows a different methods and pulses and in tandem, and then on the receiver side is well, there is some interferometry to detect which is the pulse, and I mean, and there is also time integrated on this protocol.
The challenge is with a fiber is very difficult to maintain the polarization state that you send. So polarization is much more, it's not really well suited to fibers. There are a few other schemes, but coherent one-way is pretty popular for the commercial system. They don't quite tell you what they use either, do they?
Well, yeah, there is more. What I understand is that PP84 is more information theoretical secure than the coherent one wave. But yeah, as you mentioned, the implementation is not that simple for the PP84 based on polarization. Sometimes it needs to be done with phases of signals, and yeah, there are different methods.
To show you that in our system, we have some polarization, you have to do polarization calibration.
Right, yeah.
You transmit something pure, it's necessarily get to the end in the same state. So there are, bits involved. There's always complexity.
Yeah, and there are several protocols. These are two, but there is MDI, QKD, there is even for entanglement, there's the E91.
Yeah.
So, but yeah, they all have some security proofs. And that's, yes, they are maybe good for some applications, but not for others.
All right, then I think we can move on to the next speaker.
Very different. We're not doing that. Some other
Right, okay, let's get started. Hi everyone, well done for making it here on Thursday evening. No, it's a Wednesday evening. I'm Wenmiao, one of the co-founders and the director of physical development at Quantum Dice. We are a spin out from the physics department of after actually, and we are enabling data encryption through a self-certified quantum computer. A bit about myself, I studied chemistry at AO between 2015 and 2019, and in my last term here at Oxford, I took part in Oxford US Relations student program and met my quantum program, and since then have been working on the company. I've So what we're doing is primarily solving or enabling this basically maybe appreciate being using group size code. Data is going to say is becoming more code, it's becoming more valuable. You think about it every day is huge amounts of very sensitive commercial data, other personal and personal data are constantly being generated through the request and the service creation is important. And in fact, I really think that this last year, the global average point for student engagement was the rate of So currently all this data are secured by encryption algorithms, and they all depend on the source of access to the encryption. Other solutions that we can use, but they each have their own limitations. So first, there are pseudo-random algorithms, which are based on algorithms, and hence they are more used by synthesis. Or there are also the capacity of hardware-based full-random algorithms, so for example, based on radioactive decay, or also based on calculations. Now these are hardware-based, and they are limited in terms of the generation bit, so you rely on them to make it a second. And they're also one which will transfer which will be physical validation of things. And this could be used as another process of as important to the Hence, over the past 20 years, and this industry have worked into leverage the fundamental evidence to encourage free evidence. But of course, as with any constellation of the hospital business, introducing products and products with barriers. So, for example, with regards to another one of the because of what we are planning on this in the future, and actually we grow by pollution from customers within the business. With customers who become financial markets, changes in the temperature, or specifically from the physical aggregation of the components within the organization. But this is a combination of passage around the foundation Chinese to any markets. When it's building students, so for example, in space, for example, that could be affected by just radiation. We specifically, we did more specifically about quantum entities for the frequency. They really use the way to be continuously sure that the environment will be significant. For example, the one of the workers is moving the and the last way is to have this organized system at the moment, over the devices and where this will consider something simplified on this there's always very expensive. And as if you can most space is very much limited as well as others. So it is increased the scale of increasing cost of the So what we do at Continents, we actually use the process to circulating self-certification. This was a breakthrough that was developed as part of the indigenous natural master. And this is a capacity for the So however, what it does is it continuously watches the physical class and it's able to go to top and it's just any changes to the physical commands in those it's able to post actively on most customers to ensure that the environment is that we design is only coming from customers. So we can look to see that it will first out the customers that is another hours from the customers until the applications and the So a bit more about context. Then we can look at this report. Our PNG begins with the laser, and it's light passes through two phases. So when the first phase is when the manufacturing goes to side one, and it is given by the single phase the remaining light from the laser is a very standard where there is no probability that we could by either of which to be higher this would be also the other options. This is a new process that is affected by the display, and it allows the continuous light system of which we was After this time, is pushed to the panels of the integration system. And here it's really important to things. So once the agency is created, does not necessarily represent the full ideas from the companies, but it gives us an application. So this is because the agency will be so happy with it by something completely just like this, as it will when something really happens. And second, it is physical components which introduce electrical specific example. And this additional noise is particular. Should be good must be to not like to impact the posture at the screen. So, company will be activities and this extraction algorithms, which are really mastered and is used to this skill. For example, this particular dispatch algorithm. However, the problem with the algorithm is that for very directly residency, these algorithms still require the output system of the analysis of the analytical process, which many businesses they operate are for reducing the to business as well as and business correspondence to actually create now this is where innovation for education segregation so generally, the random is the structure of this and we will use this use our where no good strings and together and the business so this is simple So the discourse is and then this continuous celebration of the occupying members of the explanation, which in time will be about people characters who are the highest level of pre-language from each explanation, the same as the system. So we think that rather than our language, this language is provided by the previous languages. And also the actual businesses have assessed data is protected by the verified supporters. So the contingency is outside by PNG overseas the interest of creators management and other people requires to keep the level of outside experience of the emphasis and consistency of the service. So the reason was the manifest includes people is the outside. First, it is a lot of things that this particular versus the reducibility for application and this they are behaving by this saving costs as long as the moving and the last one is the easy integration of the as the segregation and some different uses into the people. So in terms of our management and in terms of all of the like things out and programs and doing the past years, is actually posting on the market managers. What I think like this is very easy to identify a particular value that is interesting, but then we have to grow that specifics that are particular environments that we use the product and to be beneficial to the concept of instructions. So how we do it is our first book under this version is an external event where we will and also from the systems. So I think that we will provide when we can listen to this space and some series of opportunities with the security such as fire security, which is such as fire things happen. We will put two energy blocks of distributions will then be used to secure the pricing of the networks and centers themselves. It will review about 2 of our current projects, and we've been working with the hospital with a company that's well stable for customers. They are leading on the subject evaluation for the business, and we have developed for them the space to the energy that has a lower enough size of the market section, a higher enough renovation, so at least from the specific, and also provides an extreme space. Alongside that, we always work with the back in physical production, and the project to develop service with the is to specify how person and non-renovations differ from existing costs and outputs. So at this point, I will just have a streamline each shot. We will be working with the program for the next one, and this is an expanding kind of track out device. This has been specifically designed to use business strategies and opportunities for how this is making up this and that is to use the and whilst we're looking at that, we are a company of were buying from this, raised, element in the, we raised element between about 2.5 million, and this will allow us to hire and increase as far as I'm investment, so I'm for the technical part. This is not the space, is working with us to find the spaces applications of information. And we our QIT, which firms have right now, we limit QI's capacity to the size of the and then we limit QI's approach to the those to
See the screen?
So, good afternoon, everyone. I'm Shiny Huguessalas, and looking at circular design engineer on this. It's been almost 1 year with one dice, and it's a fantastic project. Yeah, so this is our very first hardware project, which is known as the Apex, and it can generate quantum random numbers at a very high speed of 1 meter per second, and it is compatible with the US and European standard power supply. And the main application area is data centers, telecommunication hub. So just a recap of what we screen. So it consists of all the systems that we which involves the laser, the fiber coupling, beam splitters, the photodetectors, and ADC, along with the FPGA, which is part of the post-process. So what happens is the light from the laser, which is the main source is split into 10% and 90% using beam splitters. The 90% goes into parallel photodetector, and the 10% goes into a single photodetector. And the output of this photodetectors converts this light into electrical signal, which is raw Emilio signal. And it needs to be converted to a digital version, which is done using analog to digital converter. And this digital signal is then sent into an FPGA, which does topics hashing to meet the distribution as per our need. So this is the UI of the Apex. You can see this is the section which shows the signal, and this is the section which shows the discrete. And right now what you see is the input channel, which is the live output from the ADC. That is, these are basically ADC samples at a very high speed. And it's quite random. And what you see on the right side is the histogram, which is the distribution. So as you can see, the Gaussian distribution, where the LWP at one point and then slowly fading out on the outlier. So
is the ADC channel, which is the digital signal, is then converted into byte representation using FPGA, using top extraction. And what you see here, each line is actually the byte representation, which is 8-bit representation from 0 to 55. And on the right side, you can see the top extraction has made the probability black, which means it's equally likely for the randomness to happen from 0 to 55. So assume it's 0, the randomness can happen anywhere in a single bit. So that's where the randomness system works. Now, right now I was talking about the 90% of the line that's been taken out from the single user source. Let's quickly take a look at the remaining 10%, which can be technical. So what you see is actually the 10% of the line converted to a DC signal. So this is called a self-certification panel, which basically is used to monitor on a live. So it's basically used to monitor the performance of the laser. So this is where quantum light is being used. And if there is any manipulation that happens with the laser power, it is equally likely will happen with the certification channel and the encryption channel, because the certification and the encryption channel signals are coming from the same laser. The lasers, as we know, are coherent sources, so it will be like correlated. And yeah, so that's it. Thank you so much for your time. Does anyone have any doing the flattening the lines? Thank you also for coming. Thank you very much for organizing this and bringing this together. Dominic, thank you for something. Thanks to everyone for its leaders, please.
But you design your cheaper in silicon for everybody. You know, the
Which ones?